Hello. This is video number 44. I got a little bit of a head start. I've already numbered it 44. This is video 44. And this is an even smaller version of the graph that we ended with in video 43. And just because I can't behave myself, I am so ashamed, I even put another note on it. All the other stuff, all the distances stayed the same. A to D is still 40. A to C is 100. A to B is the updated 500. Well, updated. It's now the original 500. D to C is 10, C to B is 30. I hope I copied that correctly. And then this new node came out of nowhere. E to A is 7, and E to B is 12. Those are enticing, juicy little weights on E, aren't they? I bet those are going to show up pretty soon. Now, what I'm going to do this time is be a little more deliberate about what it was I was talking through in the previous example. And by that I mean, let's keep up with what's going on in the node structures. That's where almost all the activity of this algorithm takes place. And you'll see what I mean as soon as I get this done. This looks like a 2D array or something, but it's not. This is like a 1D array of nodes, and the node values, the nodes are going to have fields in them that are updated perhaps several times as we're walking through this. And you'll see what I'm talking about once I stop talking and keep writing. Node A, node B, node C, node D, node E. And again, don't think of this as a two-dimensional table. This is the old-fashioned variable trace where I have the value of A, and I've left myself room to mark it out and update the value there several times. Now, I'm not even going to label the fields. Maybe that will be inferred. Maybe I'm going to regret that. But the distance to each node until further notice, the initialization of this is going to be, until I know better, each one of these nodes is an infinite distance away from the start node. Infinity. And if you're worried about, you know what, I've never set a variable to infinity in a C++ program. That's a technical detail. We can worry about that later. You can set it to 99,999,999 if you want to. You could have, actually, separately, you could have a field, a Boolean field that is infinite. And if that's true, then the distance is an infinite number. It's a separate field from the integer value that represents the distance. I'm getting way too specific about this, but don't worry about that. You can represent infinity any way you want. We're going to start at node A. Start, I'll label it. Well, you can put that on my table. Oh, I called it a table. I didn't mean to. I'm sorry. I'll put it on my trace over here. Start at A. What's the significance of that? Well, if we start at A, we know the distance from A to itself is 0. So that's one that we can update. And start at A is set its distance to 0, and that's the smallest one. 0 certainly less than all those infinite numbers over there. Freeze. I'm going to abbreviate. F-R-E-Z. Freeze is for freeze. Freeze A. And that means I'll officially put a box around it. You shall not be updated from this point further. And I didn't leave room over here to update the distances on the graph, and I'm sorry about that already. But we'll just have to go with it. Freeze A, update. Yeah, this tiny, I guess I'm so paranoid about running out of space, I'm writing everything so small. This says update A's ADJ list. Let me read this back. I know this is so small. We're starting at A. So the distance from A to itself is 0. That's done and done. We freeze A. I should have put that on the same line. Freeze A means we now officially know the shortest distance from that to itself. We're not going to even look at it anymore. Update A's adjacency list means we look at all the different nodes I can get to from A, which would be D and C and B, but not E. That goes the wrong direction. So I offer them, would you like to accept this shorter distance? And who are we going to offer to? Let's offer to D first. I can offer you 0, the distance to A, plus 40 more to get to D. So here, D, do you like this? 0 plus 40. And what do I mean by, do you like this? Like this means, is that shorter than the distance I already know about for myself? And in fact, well, yes, indeed. 0 plus 40, that's a lot less than infinity, last time I checked. So yes, check mark, it will accept that. 40. And that 40 represents the distance. The shortest distance I know about so far from D back to node A. Now, another thing, I'm going to cram this in here. Man, this might not even be enough space. I'm going to put crumb, C-R-U-M-B, a crumb field, A. Why? Well, as this graph gets bigger and more complex, we don't want to wiggle our way through the graph finding all these shortest paths for nothing. It would be nice to know what the shortest path actually is. The shortest path to node M is when I come through L and Z and Q and B and all that other stuff. It would be nice to know the path that I took to get there. Sort of like it's nice to know not only where the needle is in the haystack, it's nice to know how to get there from the starting point. That's what we're doing. So the crumb is like, it's almost like a backward pointer. I shudder to utter that word because it's not a pointer. We just put the index number of that node, and now we know how we got the distance to 40. Stop talking, start writing. So we offer D an update. Let's offer C an update. C, do you like 0 plus 100? Is that better than the distance you already know about? Yes, says node C. That's node C talking. It will update. It gets an updated distance of 100. Also with the crumb, already I'm abbreviating. Crumb A. I know of a short distance of 100 that comes directly from node A. This is the most recent node on the path to get to me with that short distance that I know about. Even B, let's offer B a distance. I can sell you a path, sell you a ticket from A to B for only $500, or maybe that's in thousands, $500,000, who cares? 0 plus 500. Do you like that, node B? Why, yes, that's better than the infinity, I know. I should be crossing these out. It's a replacement for the infinite distance that we already knew about. Yeah, 500, even though that doesn't sound so good, it's better than what I knew about. And the crumb. Crumb is a... What have we got so far? We froze A. We know for a fact we're not going to improve on that distance for A. And we updated. We looked at all the nodes we can get to with one more step, one more arc. We looked at all of those we could get to from A and offered them this distance. Do you like this better than the distance you know about already? And they all said yes. In this case, all three of them said yes. That iteration of this update stage is done. So I'm going to draw a dotted line, which again, I apologize, it makes it look like a two-dimensional array. It ain't. This is a variable trace. These values in these nodes got updated. Who's next? Well, here's the point where we go through and look and see, well, who has the shortest unfrozen distance? Who has the smallest, the closest unfrozen distance back to A? Our candidates are B. B says, I can get there, we can get to me with only 500 or whatever's. C says you can get to me with 100, and D says you can get to me with 40. We have a clear winner. Our clear winner is D. So we'll freeze D, F-R-E-Z, short for freeze, freeze D, which means I now pronounce 40 to be the shortest distance, the shortest path in the graph from the starting point A to node D. And it is, for the reasons stated earlier. If there were a shorter path, it would have to come through either B or C or E, and there is no shorter path coming through B or C or E because they're already further away than D. I'm going to stop saying that. And you know what? I'm going to bring the crumb down along with me. C-R-A. This, it's not a new value I set here. This is just officially freezing this. How do I officially freeze a field in a node? Feels like another Boolean variable coming on, huh? Is frozen. True or false? I just now set is frozen for node D to true, which means I'm no longer even going to offer it any updates. You've already got yours. Leave me alone. I'm trying to update all these other nodes. So after we freeze D, comma, we need to update everything in D's adjacency list. So update, who is in D's adjacency list? Not a whole lot. Update C, that's it. If we look at our tiny little graph, D, you're now frozen. You know what? I can at least double circle the ones that are frozen to know that I'm not even supposed to look at them anymore. Can I update distances from D? Yes. D can offer C an update, which will be the distance to D that we just now froze, 40, plus the additional distance, the additional cost of the leg from D to C, which is 10. Hey C, do you like this distance? 10 plus 40, which is also known as 50. Is that shorter than the path you already know? If the answer is yes, then you're out of here. Take your crumb with you. Yeah, we can update that. We like the 50. We like the 50, and the crumb is now D, because that's the one that we're radiating out from. CRD, crumb D. Okay? And that's it. That's the only node in the adjacency list for D, I believe. So, thus endeth the second iteration. The next iteration, what's the first step at the beginning of the iteration? The first step is to go shopping and try to find a node that doesn't have a frozen distance yet, and it's the smallest such node. The one unfrozen node that is closest to the starting point A. And we get three choices. Either the 500 is the shortest, or the 50 is the shortest, or the infinity is the shortest. Tough choice. I think let's freeze C. I almost said D. D's the crumb. Let's freeze C. Freeze C. I now pronounce this to be the shortest distance we are ever going to see to node C. And in fact, it is. We could go through a formal mathematical proof, but we don't have time. I'll blame the module. Thanks, 2020. Okay, we freeze D with its crumb. No, we freeze C with a crumb of D. And update any nodes that are in the adjacency list of C. We try to offer them. Any nodes that are adjacent to C that are not yet frozen, we'll offer them a better distance if we can. Update whatever nodes are in the adjacency list. You know, this graph is just so small. We're shooting flies with elephant guns here. There's so much to this algorithm that might not show up in this example. We'll have to do another example. Okay, let's see. From D, we're updating from C. From C, I can go to B with an additional 30. So to B, let's offer the 50 that we know about. That's the distance to C. The additional hop from C over to B is 30. 50 plus 30. How you like them apples, node B? Well, 50 plus 30, that's only 80. That's better than the 500 I already knew about. So yeah, I'm in. Count me in. 80. I like 80 as my distance. And the crumb field, the immediate predecessor on the path for that particular value is C. That's it. There's only one node in the adjacency list. Yeah, this example is too small. But still, I hope you're getting the general idea of what's going on here. This is not a two-dimensional array, your eyes to see view. This is the value of the fields of node B marked out and updated as we find better and better ways to get back to the source. And that, okay, I think everybody's X'd out. Here we go again. Who did I update? I updated B. Let's go shopping. Who's even unfrozen? Who's left that's not frozen? Everybody's frozen except for B and E. And 80 is less than infinity, so 80 is the next one that gets frozen. 80 with its crumb field of C is the next frozen node. Freeze B. Yay, I got the name of the node right the first time. Freeze B, update whoever B, well, B is getting a lot of attention, but it doesn't radiate out anywhere. All arrows at B are incoming. Update none. Now, you might think update none, that must mean that we're ready to fall out of our while loop. That's the end of the iteration. Actually, no. Actually, no. It just means that we don't update any distances to things smaller than what they already know about. We can't even update infinity for E over there because we can't get to E from B. But we still need to start another iteration. How do we do that? We look to see what the smallest unfrozen distance is. The smallest unfrozen distance back to the start. In this case, everybody's frozen but E. That's our smallest unfrozen distance, infinity. And then we stop. Why do we stop? Box with a check mark in it. We stop when either all of the nodes in our entire array of node structures or list of node structures, or however we've represented the node structures, all of the nodes are either frozen or they're still an infinite distance away. In this case, that's exactly what happened. They're all frozen, and there's one that's an infinite distance away. It could have been we can have all of them frozen. All of them frozen. The other extreme would be they're all an infinite distance away. If A had no outgoing arrows, they'd all be an infinite distance away. And that's where the algorithm would end. What does that imply? That implies that this multi-circled infinity up here means that E was unreachable. A-C-H-A-B-L-E means, sorry, no airline is going to fly you to E. You can't get there from here. You'll have to swim or take a slow boat. Infinite distance, that never got updated, and all the other nodes are frozen. Part of the implication of them being frozen is we've already examined any additional nodes that we could have updated as we were freezing that node. Since E never got updated, that means you can't get there from here. We stop there, it's unreachable. All these others are frozen. Not only are they frozen, they know how to get back to the start. Did I freeze B, update none? Let's see here. B. Here's how we could use the crumb field if I've kept up with them correctly. And I hope I have. Let's say we actually want to know what the path is, the shortest path to B. Well, we look over here at the crumb field. To get to B, and this is going backwards, maybe I need to, I don't know, push these onto a stack if I want to see them in the right order. Another perilously close to implementation detail. When we froze B, we froze it with the crumb of C, which means I go back to C. C is right here. How did I get to C? Well, the shortest path to C came from D. So far, I started at B, I make a backward step to C. C makes a backward step to D. How did we freeze the distance to D? D's backward step is A. So there you go. Start at B. I'm not even looking at the graph. Start at B, backwards to C, backwards to D, backwards to A, and A was the start node, so we're done. So that's the path in reverse order, the shortest path from A to B. So much to absorb in that. And yeah, we're going to have to do an additional example, but that'll have to hold you for now. I got office hours coming up. See you online.